Chapter 1. Aircraft Engines. General Requirements. Aircraft require thrust to produce enough speed for the wings to provide lift, or enough thrust to overcome the weight of the aircraft for vertical takeoff. For an aircraft to remain in level flight, thrust must be provided that is equal to, and in the opposite direction of the aircraft drag. This thrust, or propulsive force, is provided by a suitable type of aircraft heat engine. All heat engines have in common the ability to convert heat energy into mechanical energy by the flow of some fluid mass, generally air, through the engine. In all cases, the heat energy is released at a point in the cycle where the working pressure is high relative to atmospheric pressure. 1-1 equals 375 mile-pounds per hour. The propulsive force is obtained by the displacement of the working fluid. Again, atmospheric air. This air is not necessarily the same air used within the engine. By displacing air in a direction opposite to that in which the aircraft is propelled, thrust can be developed. This is an application of Newton's third law of motion. It states that for every action there is an equal and opposite reaction. So, as air is being displaced to the rear of the aircraft is moved forward by this principle. One misinterpretation of this principle is air is pushing against the air behind the aircraft, making it move forward. This is not true. Rockets in space have no air to push against, yet they can produce thrust by using Newton's third law. Atmospheric air is the principal fluid used for propulsion in every type of aircraft powerplant except the rocket, in which the total combustion gases are accelerated and displaced. The rocket must provide all the fuel and oxygen for combustion, and does not depend on atmospheric air. A rocket carries its own oxidizer rather than using ambient air for combustion. It discharges the gaseous byproducts of combustion through the exhaust nozzle at an extremely high velocity, action, and it is propelled in the other direction, reaction. The propellers of aircraft powered by reciprocating, or turboprop engines accelerate a large mass of air at a relatively lower velocity by turning a propeller. The same amount of thrust can be generated by accelerating a small mass of air to a very high velocity. The working fluid, air, used for the propulsive force is a different quantity of air than that used within the engine to produce the mechanical energy to turn the propeller. Turbojets, ramjets, and pulse jets are examples of engines that accelerate a smaller quantity of air through a large velocity change. They use the same working fluid for propulsive force that is used within the engine. One problem with these types of engines is the noise made by the high-velocity air exiting the engine. The term turbojet was used to describe any gas turbine engine, but with the differences in gas turbines used in aircraft, this term is used to describe a type of gas turbine that passes all the gases through the core of the engine directly. Turbojets, ramjets, and pulse jets have very little to no use in modern aircraft due to noise and fuel consumption. Small general aviation aircraft use mostly horizontally opposed reciprocating piston engines, while some aircraft still use radial reciprocating piston engines. Their use is very limited. Many aircraft use a form of the gas turbine engine to produce power for thrust. These engines are normally the turboprop, turboshaft, turbofan, and a few turbojet engines. Turbojet is the former term for any turbine engine. Now that there are so many different types of turbine engine, the term used to describe most turbine engines is gas turbine engine. All four of the previously mentioned engines belong to the gas turbine family. All aircraft engines must meet certain general requirements of efficiency, economy, and reliability, besides being economical in fuel consumption. An aircraft engine must be economical in the cost of original procurement and the cost of maintenance, and it must meet exacting requirements of efficiency and low weight to horsepower ratio. It must be capable of sustained high power output with no sacrifice in reliability. It must also have the durability to operate for long periods of time between overhauls. It needs to be as compact as possible, yet have easy accessibility for maintenance. It is required to be as vibration-free as possible, and be able to cover a wide range of power output at various speeds and altitudes. These requirements dictate the use of ignition systems that deliver the firing impulse to the spark plugs at the proper time in all kinds of weather and under other adverse conditions. Engine fuel delivery systems provide metered fuel at the correct proportion of fuel/air ingested by the engine regardless of the altitude, or type of weather in which the engine is operated. The engine needs a type of oil system that delivers oil under the proper pressure to lubricate and cool all of the operating parts of the engine when it is running. Also, it must have a system of damping units to damp out the vibrations of the engine when it is operating. Power and weight. The useful output of all aircraft powerplants is thrust, the force which propels the aircraft. Since the reciprocating engine is rated in brake horsepower, bhp, the gas turbine engine is rated in thrust horsepower, thp. thp equals thrust times aircraft speed, miles per hour, 375 mile-pounds per hour. The value of 375 mile-pounds per hour is derived from the basic horsepower formula as follows. 1 HP equals 33,000 foot-pounds per minute. 33,000 times 60 equals 1,980,000 foot-pounds per hour. 1,980,000. 5,280 foot in a mile. 1 horsepower equals 33,000 foot-pounds per minute, or 375 mil-pounds per hour. Under static conditions, thrust is figured as equivalent to approximately 2.6 pounds per hour. If a gas turbine is producing 4,000 pounds of thrust and the aircraft in which the engine is installed is traveling at 500 miles per hour, the THP is 4,000 times 500 equals 5,333.33 thp 375. 1-2. It is necessary to calculate the horsepower for each speed of an aircraft, since the horsepower varies with speed. Therefore, it is not practical to try to rate or compare the output of a turbine engine on a horsepower basis. The aircraft engine operates at a relatively high percentage of its maximum power output throughout its service life. The aircraft engine is at full power output whenever a takeoff is made. It may hold this power for a period of time up to the limits set by the manufacturer. The engine is seldom held at a maximum power for more than 2 minutes, and usually not that long. Within a few seconds after liftoff, the power is reduced to a power that is used for climbing, and that can be maintained for longer periods of time. After the aircraft has climbed to cruising altitude, the power of the engines is further reduced to a cruise power which can be maintained for the duration of the flight. If the weight of an engine per brake horsepower, called the specific weight of the engine, is decreased, the useful load that an aircraft can carry and the performance of the aircraft obviously are increased. Every excess pound of weight carried by an aircraft engine reduces its performance. Tremendous improvement in reducing the weight of the aircraft engine through improved design and metallurgy has resulted in reciprocating engines with a much improved power-to-weight ratio. Specific weight. Fuel economy. The basic parameter for describing the fuel economy of aircraft engines is usually specific fuel consumption. Specific fuel consumption for gas turbines is the fuel flow measured in pounds/hour, divided by thrust, pounds, and for reciprocating engines the fuel flow, pounds/hour, divided by brake horsepower. These are called thrust-specific fuel consumption and brake-specific fuel consumption, respectively. Equivalent specific fuel consumption is used for the turboprop engine, and is the fuel flow in pounds per hour divided by a turboprop's equivalent shaft horsepower. Comparisons can be made between the various engines on a specific fuel consumption basis. At low speed, the reciprocating and turboprop engines have better economy than the pure turbojet or turbofan engines. However, at high speed, because of losses in propeller efficiency, the reciprocating or turboprop engine's efficiency becomes limited above 400 miles per hour, less than that of the turbofan. Equivalent specific fuel consumption is used for the turboprop engine, and is the fuel flow in pounds per hour divided by a turboprop's equivalent shaft horsepower. Comparisons can be made between the various engines on a specific fuel consumption basis. Durability and reliability. Durability and reliability are usually considered identical factors, since it is difficult to mention one without including the other. An aircraft engine is reliable when it can perform at the specified ratings in widely varying flight attitudes, and in extreme weather conditions. Standards of powerplant reliability are agreed upon by the Federal Aviation Administration, FAA, the engine manufacturer, and the airframe manufacturer. The engine manufacturer ensures the reliability of the product by design, research, and testing. Close control of manufacturing and assembly procedures is maintained, and each engine is tested before it leaves the factory. Durability is the amount of engine life obtained while maintaining the desired reliability. The fact that an engine has successfully completed its type or proof test indicates that it can be operated in a normal manner over a long period before requiring overhaul. However, no definite time interval between overhauls is specified or implied in the engine rating. The time between overhauls, BO, varies with the operating conditions, such as engine temperatures, amount of time the engine is operated at high power settings, and the maintenance received. Recommended BOs are specified by the engine manufacturer. Reliability and durability are built into the engine by the manufacturer, but the continued reliability of the engine is determined by the maintenance, overhaul, and operating personnel. Careful maintenance and overhaul methods, thorough periodical and per-flight inspections, and strict observance of the operating limits established by the engine manufacturer make engine failure a rare occurrence. Operating flexibility. Operating flexibility is the ability of an engine to run smoothly and give desired performance at all speeds from idling to full power output. The aircraft engine must also function efficiently through all the variations in atmospheric conditions encountered in widespread operations. Compactness. To effect proper streamlining and balancing of an aircraft, the shape and size of the engine must be as compact as possible. In single-engine aircraft, the shape and size of the engine also affect the view of the pilot, making a smaller engine better from this standpoint, in addition to reducing the drag created by a large frontal area. Weight limitations, naturally, are closely related to the compactness requirement. The more elongated and spread out an engine is, the more difficult it becomes to keep the specific weight within the allowable limits. Powerplant selection. Engine-specific weight and specific fuel consumption were discussed in the previous paragraphs, but for certain design requirements, the final powerplant selection may be based, 1-3, on factors other than those that can be discussed from an analytical point of view. For that reason, a general discussion of powerplant selection follows. For aircraft whose cruising speed does not exceed 250 miles per hour, the reciprocating engine is the usual choice of powerplant. When economy is required in the low speed range, the conventional reciprocating engine is chosen because of its excellent efficiency and relatively low cost. When high altitude performance is required, the turbo-supercharged reciprocating engine may be chosen because it is capable of maintaining rated power to a high altitude, above 30,000 feet. Gas turbine engines operate most economically at high altitudes. Although in most cases the gas turbine engine provides superior performance, the cost of gas turbine engines is a limiting factor. In the range of cruising speed of 180 to 350 miles per hour, the turboprop engine performs very well. It develops more power per pound of weight than does the reciprocating engine, thus allowing a greater fuel load or payload for engines of a given power. From 350 miles per hour up to Mach 0.8-9, turbofan engines are generally used for airline operations. Aircraft intended to operate at Mach 1 or higher are powered by pure turbojet engines / afterburning, augmented engines, or low bypass turbofan engines. Types of engines. Aircraft engines can be classified by several methods. They can be classed by operating cycles, cylinder arrangement, or the method of thrust production. All are heat engines that convert fuel into heat energy that is converted to mechanical energy to produce thrust. Most of the current aircraft engines are of the internal combustion type, because the combustion process takes place inside the engine. Aircraft engines come in many different types, such as gas turbine-based, reciprocating piston, rotary, 2 or 4 cycle, spark ignition, diesel, and air or water-cooled. Reciprocating and gas turbine engines also have subdivisions based on the type of cylinder arrangement, piston, and speed range. Gas turbine. Many types of reciprocating engines have been designed. However, manufacturers have developed some designs that are used more commonly than others and are, therefore, recognized as conventional. Reciprocating engines may be classified according to the cylinder arrangement, inline, V-type, radial, and opposed, or according to the method of cooling, liquid-cooled or air-cooled. Actually, all piston engines are cooled by transferring excess heat to the surrounding air. In air-cooled engines, this heat transfer is direct from the cylinders to the air. Therefore, it is necessary to provide thin metal fins on the cylinders of an air-cooled engine in order to have increased surface for sufficient heat transfer. Most reciprocating aircraft engines are air-cooled, although a few high-powered engines use an efficient liquid cooling system. In liquid-cooled engines, the heat is transferred from the cylinders to the coolant, which is then sent through tubing and cooled within a radiator placed in the airstream. The coolant radiator must be large enough to cool the liquid efficiently. The main problem with liquid cooling is the added weight of coolant, heat exchanger, radiator, and tubing to connect the components. Liquid-cooled engines do allow high power to be obtained from the engine safely. Inline engines. An inline engine generally has an even number of cylinders. Although some 3-cylinder engines have been constructed, this engine may be either liquid-cooled or air-cooled and has only one crankshaft, which is located either above or below the cylinders. If the engine is designed to operate with the cylinders below the crankshaft, it is called an inverted engine. The inline engine has a small frontal area and is better adapted to streamlining. When mounted with the cylinders in an inverted position, it offers the added advantages of a shorter landing gear and greater pilot visibility. With increase in engine size, the air-cooled inline type offers additional problems to provide proper cooling. Therefore, this type of engine is confined to low and medium horsepower engines used in very old light aircraft. Opposed or O-type engines. The opposed type engine has 2 banks of cylinders directly opposite each other with a crankshaft in the center. Figure 1-1. The pistons of both cylinder banks are connected to the single crankshaft. Although the engine can be either liquid-cooled or air-cooled, the air-cooled version is used predominantly in aviation. It is generally mounted with the cylinders in a horizontal position. The opposed type engine has a low weight-to-horsepower ratio, and its narrow silhouette makes it ideal for horizontal installation on the aircraft wings, twin-engine applications. Another advantage is its low vibration characteristics. Figure 1-1. A typical 4-cylinder opposed engine. 1-4. V-type engines. In V-type engines, the cylinders are arranged in 2 inline banks generally set 60 degrees apart. Most of the engines have 12 cylinders, which are either liquid-cooled or air-cooled. The engines are designated by a V followed by a dash and the piston displacement in cubic inches. For example, V1710. This type of engine was used mostly during the Second World War and its use is mostly limited to older aircraft. Radial engines. The radial engine consists of a row, or rows, of cylinders arranged radially about a central crankcase. Figure 1-2. This type of engine has proven to be very rugged and dependable. The number of cylinders which make up a row may be 3, 5, 7, or 9. Some radial engines have 2 rows of 7 or 9 cylinders arranged radially about the crankcase, one in front of the other. These are called double arrow radials. Figure 1-3. One type of radial engine has 4 rows of cylinders with 7 cylinders in each row for a total of 28 cylinders. Radial engines are still used in some older cargo planes, warbirds, and crop spray planes. Although many of these engines still exist, their use is limited. The single-row, 9-cylinder radial engine is of relatively simple construction, having a 1-piece nose and a 2-section main crankcase. The larger twin-row engines are of slightly more complex construction than the single-row engines. For example, the crankcase of the Wright R3350 engine is composed of the crankcase front section, 4 crankcase main sections, front main, front center, and rear main, rear cam and tappet housing, supercharger front housing, supercharger rear housing, and supercharger rear housing cover. Pratt & Whitney engines of comparable size incorporate the same basic sections, although the construction and the nomenclature differ considerably. Figure 1-2. Radial engine. Figure 1-3. Double-row radials. Reciprocating engines. Design and construction. The basic major components of a reciprocating engine are the crankcase, cylinders, pistons, connecting rods, valves, valve operating mechanism, and crankshaft. In the head of each cylinder are the valves and spark plugs. One of the valves is in a passage leading from the induction system, the other is in a passage leading to the exhaust system. Inside each cylinder is a movable piston connected to a crankshaft by a connecting rod. Figure 1-4 illustrates the basic parts of a reciprocating engine. Crankcase sections. The foundation of an engine is the crankcase. It contains the bearings and bearing supports in which the crankshaft revolves. Besides supporting itself, the crankcase must provide a tight enclosure for the lubricating oil and must support various external and internal mechanisms of the engine. It also provides support for attachment of the cylinder assemblies and the powerplant to the aircraft. It must be sufficiently rigid and strong to prevent misalignment of the crankshaft and its bearings. Cast or forged aluminum alloy is generally used for crankcase construction because it is light and strong. The crankcase is subjected to many variations of mechanical loads and other forces, since the cylinders are fastened to the crankcase. The tremendous forces placed on the cylinder tend to pull the cylinder off the crankcase. The unbalanced centrifugal and inertia forces of the crankshaft acting through the main bearing subject the crankcase to bending moments which change continuously in direction and magnitude. The crankcase. 1-5. An intake valve is needed to let the fuel/air into the cylinder. The piston, moving within the cylinder, forms one of the walls of the combustion chamber. The piston has rings which seal the gases in the cylinder, preventing any loss of power around the sides of the piston. The connecting rod forms a link between the piston and the crankshaft. The cylinder forms a part of the chamber in which the fuel is compressed and burned. An exhaust valve is needed to let the exhaust gases out. Spark plug. Crankcase. The crankshaft and connecting rod change the straight line motion of the piston to a rotary turning motion. The crankshaft in an aircraft engine also absorbs the power or work from all the cylinders and transfers it to the propeller. Figure 1-4. Basic parts of a reciprocating engine must have sufficient stiffness to withstand these bending moments without major deflections. Figure 1-5. Figure 1-5. The crankcase. If the engine is equipped with a propeller reduction gear, the front or drive end is subjected to additional forces. In addition to the thrust forces developed by the propeller under high power output, there are severe centrifugal and gyroscopic forces applied to the crankcase due to sudden changes in the direction of flight, such as those occurring during maneuvers of the airplane. Gyroscopic forces are particularly severe when a heavy propeller is installed. To absorb centrifugal loads, a large centrifugal bearing is used in the nose section. The shape of the nose or front of the crankcase section varies considerably. In general, it is either tapered or round. Depending upon the type of reciprocating engine, the nose or front area of the crankcase varies somewhat. If the propeller is driven directly by the crankshaft, less area is needed for this component of the engine. The crankcases used on engines having opposed or inline cylinder arrangements vary in form for the different types of engines, but in general they are approximately cylindrical. One or more sides are surfaced to serve as a base to which the cylinders are attached by means of cap screws, bolts, or studs. These accurately machined surfaces are frequently referred to as cylinder pads. If the propeller is driven by reduction gearing, gears that slow down the speed of the propeller less than the engine, more area is required to house the reduction gears. A tapered nose section is used quite frequently on direct drive, low-powered engines, because extra space is not required to house the 1-6 propeller reduction gears. Crankcase nose sections are usually cast of either aluminum alloy or magnesium. The crankcase nose section on engines that develop from 1000 to 2500 HP is usually larger to house reduction gears, and sometimes ribbed to get as much strength as possible. The governor is used to control propeller speed and blade angle. The mounting of the propeller governor varies. On some engines, it is located on the rear section, although this complicates the installation, especially if the propeller is operated or controlled by oil pressure. Because of the distance between the governor and propeller, where hydraulically operated propellers are used, it is good practice to mount the governor on the nose section as close to the propeller as possible to reduce the length of the oil passages. The governor is then driven either from gear teeth on the periphery of the bell gear or by some other suitable means. This basic arrangement is also used for turboprops. On some of the larger radial engines, a small chamber is located on the bottom of the nose section to collect the oil. This is called the nose section oil sump. Since the nose section transmits many varied forces to the main crankcase or power section, it must be secured properly to transmit the load sufficiently. The machined surfaces on which the cylinders are mounted are called cylinder pads. They are provided with a suitable means of retaining or fastening the cylinders to the crankcase. The general practice in securing the cylinder flange to the pad is to mount studs in threaded holes in the crankcase. The inner portion of the cylinder pads are sometimes chamfered or tapered to permit the installation of a large rubber O-ring around the cylinder skirt, which effectively seals the joint between the cylinder and the Crankcase pads against oil leakage. Because oil is thrown about the crankcase, especially on inverted inline and radial type engines, the cylinder skirts extend a considerable distance into the crankcase sections to reduce the flow of oil into the inverted cylinders. The piston and ring assemblies must be arranged so that they throw out the oil splashed directly into them. Mounting lugs are spaced about the periphery of the rear of the crankcase or the diffuser section of a radial engine. These are used to attach the engine assembly to the engine mount or framework provided for attaching the powerplant to the fuselage of single-engine aircraft, or to the wing nacelle structure of multi-engine aircraft. The mounting lugs may be either integral with the crankcase or diffuser section or detachable. As in the case of flexible or dynamic engine mounts, the mounting arrangement supports the entire powerplant including the propeller, and therefore is designed to provide ample strength for rapid maneuvers or other loadings, because of the elongation and contraction of the cylinders. The intake pipes which carry the mixture from the diffuser chamber through the intake valve ports are arranged to provide a slip joint which must be leak-proof. The atmospheric pressure on the outside of the case of an unsupercharged engine is higher than on the inside, especially when the engine is operating at idling speed. If the engine is equipped with a supercharger and operated at full throttle, the pressure is considerably higher on the inside than on the outside of the case. If the slip joint connection has a slight leakage, the engine may idle fast due to a slight leaning of the mixture. If the leak is quite large, it may not idle at all. At open throttle, a small leak probably would not be noticeable in operation of the engine, but the slight leaning of the fuel/air mixture might cause detonation or damage to the valves and valve seats. On some radial engines, the intake pipe has considerable length, and on some inline engines, the intake pipe is at right angles to the cylinders. In these cases, flexibility of the intake pipe or its arrangement eliminates the need for a slip joint. In any case, the engine induction system must be arranged so that it does not leak air, and change the desired fuel/air ratio. Accessory section. The accessory rear section usually is of cast construction and the material may be either aluminum alloy, which is used most widely, or magnesium, which has been used to some extent. On some engines, it is cast in one piece, and provided with means for mounting the accessories, such as magnetos, carburetors, fuel, oil, vacuum pumps, starter, generator, tachometer drive, etc. in the various locations required to facilitate accessibility. Other adaptations consist of an aluminum alloy casting, and a separate cast magnesium cover plate on which the accessory mounts are arranged. Accessory drive shafts are mounted in suitable drive arrangements that are carried out to the accessory mounting pads. In this manner, the various gear ratios can be arranged to give the proper drive speed to magnetos, pumps, and other accessories to obtain correct timing or functioning. Accessory gear trains. Gear trains, containing both spur and bevel type gears, are used in the different types of engines for driving engine components and accessories. Spur type gears are generally used to drive the heavier loaded accessories, or those requiring the least play or backlash in the gear train. Bevel gears permit angular location of short stub shafts leading to the various accessory mounting pads. Unopposed, reciprocating engines. The accessory gear trains are usually simple arrangements. Many of these engines use simple gear trains to drive the engine's accessories at the proper speeds. 1-7. Crankshafts. The crankshaft is carried in a position parallel to the longitudinal axis of the crankcase and is generally supported by a main bearing between each throw. The crankshaft main bearings must be supported rigidly in the crankcase. This usually is accomplished by means of transverse webs in the crankcase, one for each main bearing. The webs form an integral part of the structure and, in addition to supporting the main bearings, add to the strength of the entire case. The crankcase is divided into two sections in a longitudinal plane. This division may be in the plane of the crankshaft, so that one half of the main bearing, and sometimes camshaft bearings, are carried in one section of the case, and the other half in the opposite section. Figure 1-6. Another method is to divide the case in such a manner that the main bearings are secured to only one section of the case on which the cylinders are attached, thereby providing means of removing a section of the crankcase for inspection without disturbing the bearing adjustment. The crankshaft is the backbone of the reciprocating engine. It is subjected to most of the forces developed by the engine. Its main purpose is to transform the reciprocating motion of the piston and connecting rod into rotary motion for rotation of the propeller. The crankshaft, as the name implies, is a shaft composed of one or more cranks located at specified points along its length. The cranks, or throws, are formed by forging offsets into a shaft before it is machined. Since crankshafts must be very strong, they generally are forged from a very strong alloy, such as chromium nickel molybdenum steel. A crankshaft may be of single-piece or multi-piece construction. Figure 1-7 shows two representative types of solid crankshafts used in aircraft engines. The four-throw construction may be used either on four-cylinder horizontal opposed, or four-cylinder inline engines. The six-throw shaft is used on six-cylinder inline engines, 12-cylinder V-type engines, and six-cylinder opposed engines. Crankshafts of radial engines may be the single-throw, two-throw, or four-throw type, depending on whether the engine is the single-row, twin-row, or four-row type. A single-throw radial engine crankshaft is shown in Figure 1-8. No matter how many throws it may have, Each crankshaft has three main parts: a journal, crank pin, and crankcheek, counterweights. Main bearing surface, camshaft bearings, generator prop shaft, connecting rod, crankcase, left half, parting surface, crankcase, right half, magneto, transverse webs, crankshaft, cylinder, tachometer, starter, camshaft, accessory case assembly, oil pump, oil sump. Figure 1-6, typical opposed engine exploded into component assemblies. 1-8, induction system. 1. 4. Cylinders crank arm. 1. 4. 180 degrees, 180 degrees, journal. 2, 3, 3, 4. 2, 3, 3, 4. 1, 2, 5, 6. 120 degrees, 5. 2, 120 degrees, 120 degrees, 1, 6. Figure 1-7. Solid types of crankshafts. Crank pin, journal, crankcheek, counterweight damping weights. Figure 1-8. A single-throw radial engine crankshaft, and dampers, although not a true part of the crankshaft, are usually attached to it to reduce engine vibration. The journal is supported by, and rotates in, a main bearing. It serves as the center of rotation of the crankshaft. It is surface hardened to reduce wear. The crank pin is the section to which the connecting rod is attached. It is off-center from the main journals and is often called the throw. Two crank cheeks and a crank pin make a throw. When a force is applied to the crank pin in any direction other than parallel or perpendicular to, and through the center line of the crankshaft, it causes the crankshaft to rotate. The outer surface is hardened by nitriding to increase its resistance to wear and to provide the required bearing surface. The crank pin is usually hollow. This reduces the total weight of the crankshaft, and provides a passage for the transfer of lubricating oil. On early engines, the hollow crank pin also served as a chamber for collecting sludge, carbon deposits, and other foreign material. Centrifugal force threw these substances to the outside of the chamber and kept them from reaching the connecting rod bearing surface. Due to the use of ashless dispersant oils, newer engines no longer use sludge chambers. On some engines, a passage is drilled in the crank cheek to allow oil from the hollow crankshaft to be sprayed on the cylinder walls. The crank cheek connects the crank pin to the main journal. In some designs, the cheek extends beyond the journal and carries a counterweight to balance the crankshaft. The crank cheek must be of sturdy construction to obtain the required rigidity between the crank pin and the journal. In all cases, the type of crankshaft and the number of crank pins must correspond with the cylinder arrangement of the engine. The position of the cranks on the crankshaft in relation to the other cranks of the same shaft is expressed in degrees. The simplest crankshaft is the single throw, or 360 degrees type. This type is used in a single-row radial engine. It can be constructed in one or two pieces. Two main bearings, one on each end, are provided when this type of crankshaft is 1-9. Used. The double throw or 180 degrees crankshaft is used on double-arrow radial engines. In the radial type engine, one throw is provided for each row of cylinders. Crankshaft balance. Excessive vibration in an engine not only results in fatigue failure of the metal structures, but also causes the moving parts to wear rapidly. In some instances, excessive vibration is caused by a crankshaft that is not balanced. Crankshafts are balanced for static balance and dynamic balance. A crankshaft is statically balanced when the weight of the entire assembly of crank pins, crank cheeks, and counterweights is balanced around the axis of rotation. When checked for static balance, it is placed on two knife edges. If the shaft tends to turn toward any one position during the test, it is out of static balance. Dynamic dampers. A crankshaft is dynamically balanced when all the forces created by crankshaft rotation and power impulses are balanced within themselves so that little or no vibration is produced when the engine is operating. To reduce vibration to a minimum during engine operation, dynamic dampers are incorporated on the crankshaft. A dynamic damper is merely a pendulum that is fastened to the crankshaft, so that it is free to move in a small arcade. It is incorporated in the counterweight assembly. Some crankshafts incorporate two or more of these assemblies, each being attached to a different crankcheek. The distance the pendulum moves and, thus, its vibrating frequency corresponds to the frequency of the power impulses of the engine. When the vibration frequency of the crankshaft occurs, the pendulum oscillates out of time with the crankshaft vibration, thus reducing vibration to a minimum. The construction of the dynamic damper used in one engine consists of a movable slotted steel counterweight attached to the crankcheek. Two spool-shaped steel pins extend into the slot and pass through oversized holes in the counterweight and crankcheek. The difference in the diameter between the pins and the holes provides a pendulum effect. An analogy of the functioning of a dynamic damper is shown in Figure 1-9, connecting rods. The connecting rod is the link that transmits forces between the piston and the crankshaft. Figure 1-10, connecting rods must be strong enough to remain rigid under load, and yet be light enough to reduce the inertia forces that are produced when the rod and piston stop, change direction, and start again at the end of each stroke. Figure 1-10, a connecting rod between the piston and crankshaft. There are four types of connecting rod assemblies. Figure 1-11, 1. Plane 2. Fork and blade 3, master and articulated 4. Split type, hand pump bellow. Pendulum length hand pump bellow. Figure 1-9. Principles of a dynamic damper. 1-10. Blade rod.